Hey, AP Physics students. This is Mr. Everly talking to you on this weird snow, ice, whatever kind of day this is. Whatever it is, we're not in school today. I'd like to give you a very short explanation of what is meant by electric flux. Now, first hour saw some of this already on Tuesday, but I will get to some examples at the end that we did not get to in class. So if the first hour folks want to fast forward through some of this, that's just fine. Imagine that in my room, we've got some airflow. The Latin word for flow is flux. So in Latin, we'd say, if I set up a fan over here somewhere and blow some air across the room, that we've got some air flux. Now, suppose I've got a little window for the air to go through. So I got this little wire rectangle that I set like right here, perpendicular to the airflow. And I'd like to know how much air goes through that little rectangle every second. So you'd say, okay, let's see. The speed of the air is like 3 centimeters a second. Let's say our rectangle there, its height we'll call B, and say that's like let's say 10 centimeters. And A is 5 centimeters. Nice numbers. If air flows through here at 3 centimeters per second, that means it's kind of like we have a rectangular solid of air 3 centimeters long, because this air travels 3 centimeters in 1 second. So if I want to know how much air goes through there, it's really easy. We could say the air flux, yes, the symbol for flux is the capital letter phi or phi in the Greek alphabet. I'm going to say, all right, it's just this times this times this. Now what I'm really doing is saying it's the area of my little window times the speed. Okay, or if you don't mind me switching the order, this is area and this is velocity. So we could then say that the amount of air flowing through my little window here is V times A. Okay, so like 150 cubic centimeters per second in this example. Okay, V is a vector. We're going to turn A into a vector too, which is kind of weird. Physics guys and gals are kind of weird people. So what we're doing for this particular example or this particular application is saying that area is a vector perpendicular to the little window we choose. So we got our little window, we draw an arrow perpendicular to the face of our window, and we make the arrow long enough to represent this 50 square centimeters. That's the area. Okay, there's a good reason for that, even though it seems kind of weird right now. Suppose, though, that I take my little window here and stick it into the air so that it is parallel to the air. So the face of the window is parallel to the air. We would say, wait, the amount of air passing through my little window is exactly 0 because it can't get through. If you look at it from the side of the window is parallel to the airflow. So we can't use our equation anymore. It's just 0. If we take something in between, okay, so here's our airflow, and we take our little window and put it at an angle. Okay, now the air flowing through our window is less than it was up here because it's angled. The effective window is reduced. Here the effective window is 0. Here the effective window is some fraction of the area of my rectangle. So the back side of this shape here is actually the effective area. And you go, okay, how do we calculate then this area so that we can multiply it by the velocity and get the airflow? Okay, what we're going to do is we're going to say again that the area vector is this little guy right here. Okay? And that area vector is at an angle to the flow of the air. Okay? There's theta, which happens to be this theta right here. So if this side of my window, which actually exists, is B, this side of my window is B cosine theta. Okay? I think you can convince yourself of that pretty quickly. This side is still A, so the effective area of the window that allows the air to flow through is going to be A times B cosine theta. Okay, so this is B cosine theta, this is A, so this area of the back side of this shape is AB cosine theta. That's what the air is going through. Less air is going to go through the shape when it's tilted than when its face is perpendicular to the airflow. Okay? So, in order to calculate the airflow here, I'm going to say it's V times A times the cosine of theta. Okay? Because my effective airflow is the original area of my shape times the cosine of theta. Okay? Original area, effective area. Okay? Effective area is the original area times the cosine of theta. Now, what I'm actually doing here with this vector and the cosine of theta is a dot product. What we mean to say here is that the air flux through our little window is going to be V dot A. That's the definition of dot product. Theta is the angle between the direction of V and the direction of A. Okay? Now, this unit isn't about airflow. What it is about is electric fields. So how do we apply this to electric fields? We do it the exact same way. We say, imagine there's an electric field passing through this space. Okay? If we imagine a little window of area here with an area vector A that's parallel to it, it's easy to calculate the flux. Instead of V, we're going to have E dot A. Okay? If we take our little window and tilt it so that it's parallel to our field lines, no field lines will pass through it. If that's the case, then we've got the flux equal to E dot A, or EA cosine theta. But when theta is 90 degrees, again, here's our area vector. When the area vector is 90 degrees to E, EA cosine theta becomes 0. Okay? When the angle is 0, this guy becomes 1, and it's just E times A. When we're on an angle, the effective area is reduced. So it becomes EA cosine theta. As demonstrated before, this effective area is A times the cosine of theta. All right, the units for phi. Newtons per coulomb. Area is meters squared. There it is. We don't have a special name for it. They didn't name it after anyone famous. They just call it Newton meter squared per coulomb. Okay, that's the unit of electric flux. Also, electric flux is a scalar, which is going to make our lives a little easier later on. Being a scalar, we don't have to worry about the direction of electric flux. Okay, this is a dot product. E has a direction. The area, bizarrely, has a direction, but the electric flux, this weird symbol here, doesn't have a direction. Okay. At the moment, you might be wondering why we're defining all these things. That's coming up later. Let's do a couple of examples, and we'll call it good. All right. Here's an example of a circular plate. So this plate is seen on edge. If I were an artist, I would try to draw it like this, as a circular plate tilted in the field. But we're seeing this edge on. It has a radius of 12 centimeters. The plane of the plate is set at 30 degrees to the uniform field. And the field strength is 450 I hat, as shown in the figure. What's the flux through the plate? Okay. Our area vector points that way. Its angle to the field is 60 degrees. I'm going with 2 sig figs on this. So we're not going to use the 30 degrees. We're going to use the 60 degrees. So phi is equal to E dot A. That means it's EA cosine theta, where this is the magnitude of the field, that's the magnitude of the area, that's the angle between the two vectors, the E vector and the A vector. So 450 newtons per coulomb. Area, this is a circle now, so we have to be careful. Area of a circle is pi r squared. So I'm going to say it's pi times 0.12 meters squared times the cosine of 60 degrees. Okay, we're getting an answer of about 10 Newton meters squared per coulomb if you punch that out. Okay, so far we're just kind of going by the numbers, following this weird definition that we made earlier. Two more examples. A square plate with a side of 12 centimeters lies in the XY plane. What is the flux through the plate due to this uniform field? Okay, so if we've got X, Y, like on the floor, and Z is the corner of the wall, from the corner of the wall going upwards, you could say, hey, this square plate is sitting here on the XY axis, and this field has a component in the X direction and in the Z direction, so it's coming up at some weird angle. But they gave it to us in unit vector notation, and we're going to do a dot product. So remember, when we're doing a dot product in unit vector notation, if both vectors are unit vector notation, all we have to do is multiply the i's, multiply the j's, multiply the k's, and add them up. And remember, this is a scalar. There's going to be no direction, there's no angle, there's no I hat, j hat, k hat in our answer. Okay, so E dot A is going to look like this. We've got, for E, 70 I hat plus 0 J hat. They don't give us a J hat. Plus 90 K hat. Our area vector. Okay, our area vector is going to be 12 times 12, and it's going to point in the z direction because, again, we define our area vector as being perpendicular to the face of this square. So I'm going to say it's 0 I hat plus 0 K hat plus 0.0144 K hat. Oh, that's a J. I apologize. Okay, let me say that better. 0 I hat plus 0 J hat plus 0.0144 K hat. Sorry, misspoke. Now, remember, when you dot these unit vector notations, we go this times this. Oh, that's 0. This times this. Oh, that's 0. This times this. Oh, that's about 1.3 Newton meters squared per coulomb. What direction? It doesn't have a direction. We just dotted something. Okay? If we need some review on how to deal with unit vector notation and dot products, we can do that in class. Last one. We've got a uniform electric field parallel to the central axis of a hemisphere. So this is like a dome. Radius r as shown. What's the flux through the hemisphere? So these field lines are coming up through the hemisphere and then hitting the top, and we'd like to know what's the flux through this thing. This is extremely difficult because the flux coming through here hits at all different angles relative to the area vector. The area vector, remember, is perpendicular to the surface at any point. So now we've got all these different angles, and it's like, how are we going to do this? Call Miss Doughton in, do some major calculus with this. No. Turns out that all the electric field lines that pass through this dome must also pass through the base. Okay, so the amount of flux passing into the base must be equal to the flux passing out through the top. In other words, what's going in is got to come out. So we can say, hey, look, the flux on this thing is just going to be the area of the bottom times the E field. And that will be equal to the crazy flux coming out of the top, which is very, very difficult to calculate. This is going to be a theme of this unit, is we're going to run into some things that are almost impossible to do, and we're going to find ways around the impossible math. We're going to find tricks and be sneaky and find ways to do this that makes a little bit more sense, or at least make our lives a little easier. Okay, so we're going to say, all right, the E field times the area of just the base is going to do it for us. Okay, again, it's a scalar. We don't need a direction. One thing that we're going to define later, it's not as important now, is that when flux is going into a shape, we call that negative flux, and when it's coming out of the shape, we call it positive flux. So this is going to be a positive answer. If they were asking how much was coming into the base, we give a negative number. If we asking how much is coming out of the top, we give a positive number. That's going to be a little bit more important later than it is right now. All right.